Hi guys, Mrs. H here. Today we're going to be looking at forces. So by the end of today, we're going to be looking at how force is measured. We're going to look at the difference between contact and non-contact forces. We're going to be describing friction and how it affects motion. And then we're going to be looking at force using the equation F equals M times A. And so then we also have some key vocabulary involved as well. So what is force? So force is both has size and direction. So that means it has a magnitude or size. And remember when we talked about force of gravity, we talked about it being measured in newtons. And that was obviously named after Sir Isaac Newton, so the famous English physicist who actually figured out what all of this means. So how do we measure force? So if you look over at that diagram, that's actually a little device that is used to calibrate newtons, and it's a spring. And so if you put an object on the bottom, the spring will be calibrated to pull the force down. So we can use it to measure forces. It will also be, this is going to be looking at the size or the magnitude. Obviously, the direction you would have to be using your observation skills to determine the direction of it. So this is only to measure the magnitude. You can also use this to see how much force you need to apply to drag something across the table. So it doesn't just have to be measuring the force of weight. It can also be the force to pull an object or the force to push an object. And so we call it a Newton meter. So there's two different kinds of forces that we talk about. There's contact forces and non-contact forces. So a contact force is the objects have to be touching. So if they're touching each other, contact to contact, surface to surface, we call it contact forces. And then non-contact forces are forces that act on each other over a distance. And so that one might be seeming odd, but when we look at examples, it's like, oh, okay, yeah, I totally get that now. So magnets and gravity would be an example of non-contact force. So you can jump off of the desk and the gravitational force is going to be pulling you down. You're not touching the ground, but that force is pulling you down. Magnet, same thing. You can put a penny in front, or a nickel or a quarter or whatever, anything that's magnetized in front of a magnet, and that magnet's going to pull it towards it. So they're not touching, but the force is still acting on it. So we sometimes say there's a field or a force field. So, may the force be with you. That force would be what they're talking about is a non-contact force. Obviously, the farther the objects are, the greater the distance there is, the less the strength of the force decreases. So let's go ahead and look at these kinds of forces. So there's three main types. So magnetic, the origin is magnetism. So the action is a push or a pull. So iron and steel would be an example of these. And magnetic forces are a strong force. Electrostatic, so this is an electrical charge. That's again a push or a pull, and this is due to charged particles or charged objects. So your electrons and protons, so ions, those are charged particles. And actually you have objects moving across your cell membrane. When you get into biology, we'll discuss that. And things move in and out of the cell membrane and through the cell membrane because of those charges. So your body right now is full of electrostatic charges, which allows particles to move through your body, which allows you to function as a living organism. Those are also strong forces. And then you also have gravitational force. So these are any objects with a mass. This is a pull. All objects have these. And actually, this is considered a weak force, believe it or not. So let's go ahead and do a quick comprehension check. So let's go ahead and identify the contact forces and non-contact forces. Okay, so then let's look at friction. So friction is a type of contact force. So this is because the two objects, and this can be a solid, liquid, or gas, and these are moving. Friction is when you drag. Um, uh, drag is often considered, is not often, it's considered a friction force. So the drag from a car, that is actually friction that we're describing. So so boats will have drag on the bottom of the boat, and so that slows it down. So people wax the bottom of the boat to decrease the drag, and so the boat can go faster. You get drag on cars. So in race cars, they actually design the body of the car so it reduces the drag. Now, if you're jumping out of with a parachute, or you're sailing, the drag is used to actually move the objects, so that it's helpful there. Again, this can be through air, solid, liquid, or gas. Friction occurs. Friction acts, the friction actually is in opposite direction of the motion. So if I'm moving left, the drag would be right. This causes the objects to slow down, and the objects will convert sometimes that energy to kinetic energy into heat. So when you rub your hands together, you can feel the heat on your hands from that friction. Tires burning, so when they peel out and that smoke comes up, that's what you're seeing, is the heat being released. Friction is not always bad. Friction is good. If it wasn't for friction, it would be really difficult to walk. We'd be falling all over the place. So imagine walking on ice all the time. That would be what it would be like without friction. So we move around because of friction. So it is a good thing. In sports, they actually treads or spikes on your sports shoes. Those are to create more tread. If you're surfing, they actually wax the bottom to excuse me. Sorry about that, guys. So treads on tires, so creating friction so that we can move down the road. If you put sand down or on a slippery road, that's again to create that friction. So you see that usually in colder states, they won't put salt down, they'll actually put sand down. And that's again to help that slippery sliding from the ice that the ice creates. So friction can be helpful. It also can be unhelpful, not harmful, but unhelpful. So friction on bikes. So the friction created on those gears in a car. So that's why you want to make sure you oil your car to reduce the friction created in the engine. Same thing with your bikes. You want to make sure that you're oiling your chains to reduce that friction. So here's an example. If I want to increase my speed, I have to overcome the force of friction. However, if I want to slow down, I'm actually going to increase friction to help me slow down. So when you're pedaling on your bike and you want to change your motion, it all has to do with overcoming or using friction. If my friction and my pedal force, so how much am I thrusting how much am I pushing down on my pedal, and my friction are equal, then actually the what's considered balanced forces, which we'll talk about later. So other things we use to reduce friction, I talked about one, lubricants. Using wheels. The whole concept of a wheel is to reduce friction, creating a layer of air, so like airboats, that will actually reduce friction. The shape of the body, so like when I was talking about the cars, that will actually help reduce, or even putting a wax layer that's reducing those little fine little bumps on the surface that we don't see. The wax fills it in and creates a flat surface, creating less friction. Aerodynamics, reducing that friction when I was talking about the shape of something. So that's actually creating aerodynamic. When you put the tail on a car, that's actually creating a aerodynamic. It helps the air move through it, and so that actually reduces the friction. Planes are very aerodynamic. The design of a plane is very, very efficient to reduce drag. So we talked about this last week. So remember gravity and the weight. Weight is a force. So remember when we were describing weight, that we talked about how different planets have different gravities. So we have different weight on different planets because the pull down, the gravitational pull on each planet is different. That's why you see the pictures of the astronauts kind of bouncing along, because the gravity is so low that it's not really a hard force to overcome. Where it on the Earth, jumping, there's only so far you can jump up. Why? Because that force of gravity pulling you down, because it's a greater force. We can also look at this equation. Oh, excuse me. Wrong slide. So when we talk about a vacuum, or we talk about the rate of acceleration, well, two objects, the feather and the hammer, when they fall in air, they fall at different rates. Why? Is it that the force of gravity is different? No, because there's other forces acting on these objects besides the force of gravity. When you put them in a vacuum, they will fall at the same rate, which we have talked about in the past. Galileo actually predicted this a long time ago. So he said that the feather and the hammer would fall at the same rate, but it wasn't actually determined to be true, or actually been able to be tested until 1971 with Apollo 15. The astronaut actually dropped the feather and the hammer on the moon, and it does in fact drop at the same rate. Now, we do have devices now that create a vacuum, so you don't have to go to the moon to do that anymore. Okay, so we talked about this before. We talked about using the equation F equals m times g to calculate weight. Well, we can use that same equation to calculate the force of an object. And instead of the acceleration due to gravity, we can use acceleration of the object. So if the object is accelerating at a certain rate and it has a mass, we can calculate the force. It doesn't have to be the gravitational force. So let's look at some examples here. So here I have a person with a mass of 60 kilograms, and they're accelerating at a rate of 10 meters per second. So if I use the equation F equals m times g, or F times a, because g, remember, is acceleration. So F equals 60 times 10. So the force on this would be 60 newtons. So here's a couple practice problems I'd like you to try and see how you do on your own. And so how did you do? On the first one, we're just calculating force, so we're going to use m times a. On the second one, we have to rearrange our equation to solve for mass. So m equals F times g, or F times a. And then on the last one, we're again calculating for force, and so it'd be F equals m times a. And so over the next couple days, we're going to be looking at calculating force equals mass times acceleration. So if you have any questions, please let me know. I'm here to help. Bye, guys.